All right, hello everyone. My name is James Snell. I am coming to you with the latest Near Form Node Week webinar. Uh, we're going to be talking about HTTP2 for Node Core. A little bit of background of myself. I am on the Node Core technical team, the TSC. I've been involved with Node for a while. I'm one of those that gets paid full time to actually work on Node Core itself. So it's quite a fun and lovely thing. Uh, for the past well, maybe 6 months, 8 months, I've been working on an HTTP2 implementation with a couple of other folks working on Node. And this talk is really to kind of update on where we're at with that implementation. It's an updated talk version of the talk that I gave at Node.js Interactive in Austin last, I think, December. It's going to touch on updated status where we're at, and we're also going to talk about a little bit about the um, the current status of the implementation and the protocol itself, and kind of lay out some of the differences between the HP1 and HP2 to provide a little context for where things are at and why we're making some of the decisions that we're making. So we'll go ahead and get into it. Towards the end, I'll take some questions. You should have a questions box over in the control panel. If you have any questions, go ahead and fill that out there. Or if you @mention me on Twitter, you can ask the question there. My Twitter is there on the screen, JA Snell. I'll try to get to the questions at the end. We'll see what we can do with those. If there's too many, we'll pick the top few and go from there. So with that, let's go ahead and get on into it. Basic agenda, we're going to talk about the HP2 protocol, some of the implementation details, and then our plan for actually rolling it out and getting it into Node Core. So let's jump right in. HP version 1.1 and 2 are two very, very different things. They share a name. They share some semantics in terms of the request and response and headers and the body. But when you get into the details of the protocol, there are two very, very different things. And if you look at the specific details, they really can be considered two completely different protocols. HP2 introduces a new binary framing, which is one of the most significant differences. We'll get into that a little bit more and what that means. You can have multiple concurrent in-flight requests and responses. This is another major thing. With HP1, we had the ability to pipeline sequentially requests and responses, where you could send multiple requests, but you had to wait for the responses to come back in order. With HP2, we don't have that problem anymore. It's full multiplexing, and we have a few other new features, such as server-initiated responses or push, flow control that exists per individual stream and connection. We'll go into that a little bit more later. Prioritization, stateful header compression. I'm going to go into some detail on that because it is introduced some new requirements to the protocol that didn't exist previously. And there's some other things: item potency, protections, the ability to replay failed requests, which doesn't exist in version 1.1, and some enhanced security. Some of those I won't go into too much detail on, but we can get into later during the question and answer if anyone wants to talk about that specifically. So HP1, just as a recap, HP is essentially a text protocol. When you open a socket, you basically send a series of headers, which are just line delimited name value pairs, followed by some bit of payload, which can be text or binary, and it's all sent as a block. You can only put one out on that, on that socket at a time. Everything is line delimited with the CRLF. Any parser that's receiving these and making sense of these looks specifically for those CRLF lines, and it's a very specific format. It's also very, very efficient. The challenge with it is that because you can only have one message in each direction at any given time, when you do use pipelining, you end up with what's called a head of line blocking. You can imagine sending a large file followed by a small file. A small file may be easier to transmit, faster to transmit, but it has to wait until that large file is completely done, and that runs into all kinds of performance issues. And because of that, we end up having all kinds of workarounds where people bundle multiple files together, or they use sharding and open multiple client requests to the server. All kinds of little tricks and workarounds and things that people do. With HB2, all of that goes away because of the ability to multiplex requests over a single connection, and we'll talk about exactly how that is done in just a minute. But the HB1 protocol, it's it's fairly simple. You can open a telnet connection with a server and actually manually type a request and see the response back. It's very, very, very straightforward and very simple. HB2 adds a significantly higher level of complexity. There's a lot more going on, and it's really important to understand the details of the protocol, even if the Node implementation I'm going to show hides most of those details from you. It's important to understand what is happening there, because it's going to have a much different impact in terms of the performance profile on your Node applications. There's much more happening per tick of the event loop. So it's really important to understand the details and know what is happening under the covers. So if we look at HTTP2, it's the same message. So there's still headers, a series of name value pairs. There's still the payload. But what we're doing instead of just sending a big blob of text is we are dividing that up into discrete binary frames. And each frame has a 9-bit header, or 9-byte header. That includes the size, some flags, the type of frame it is. In the frame types, you have control frames, which are used for basically management of the session, where settings and ping and those kinds of things. Then you have header frames and data frames. Header frames, exactly as the name suggests, sends those name value pairs. The data frame sends just the chunks of data that you're sending. And rather than having to send those as one large contiguous file, a stream of data, one after the other, we can take individual chunks. Every frame has an ID, a stream ID. And you just, take an individual chunk, send it along, take the next chunk from the next request, send it along. And we can mix these things. And there is no, there's no theoretical limit really to the amount of multiplexing we can go here, other than the limit to the maximum number of streams, which is like a 31-bit number. So there's quite a few things that you can do here theoretically. Okay, a priority queue is used to determine what to send at any given time. Every stream, and a stream is a bidirectional flow. So if you imagine if you're familiar with Node, a duplex, where it is both readable and writable, or a socket, readable and writable. That's what the stream is HV2's abstraction for that. Every request and response exchange within HV2 is carried by a single stream, where the client initiates the request, opens the stream, the server uses that same stream ID to send the response. Every single one of those can have its own priority. And then you can have streams that depend on other streams. So you have prioritization groups. I won't go into all the details, it's fairly complex. But what this allows us to do, allows the server or the client to do, is determine which bits it wishes to see. So if you have a browser that has multiple tabs open, for instance, you can have a case where only the visible tab has a higher priority for data, and the tabs that aren't visible, while those connections may still be live, have a lower priority, so that data is not going to be sent as quickly. This priority queue is at the heart of HB2 in the implementation, and it's really important to understand how that works in order to get good performance out of the implementation. So let's look, just as we said, at any given time there's multiple streams. Each one of these has a distinct ID. Here I'm marking it, is stream 1, stream 3, and stream 5. Client-initiated streams are always an odd number. Server-initiated streams, what we call push, are even number. Gives you a good idea when you're debugging, kind of where that thing originated. But as we have these parallel streams of data going into the priority queue, it's going to come out in some sequence determined by that priority queue on the socket. These frames can be as small as 9 bytes, as large as 16 million bytes. And it really depends on the frame type. The protocol itself can be quite chatty. We can end up with a large number of very small frames, which is another important thing we need to keep in mind for performance. HTTP header compression is a major new feature of the protocol. And this is something that a lot of people, it's important to understand. HTTP1 is a fully stateless protocol. When you send a message from point A to point B, it doesn't retain any of that knowledge. Headers, in particular, tend to be quite wasteful. For instance, whenever you send a date in a request, which is is fairly mandatory, that every date is 29 bytes sent back and forth. The other headers, if you think like cookies or the user agent header, these are things that don't change frequently, but with every request they're sent back and forth. With HTTP2, header compression is used, stateful header compression specifically is used to limit the amount of redundant data that's sent over the wire. And it turns out to be critically important, especially when we're multiplexing, because we don't want to send the same cookie over and over and over again over the same request over 100 different multiplexed requests. So instead, we use a delta encoding and these state tables to only pass the information that has changed from one request to the next. And the data that actually is sent is further compressed using Huffman coding, allowing us to achieve significant compression ratios just for sending those headers. I'll talk about a little bit more about how that works in a second. The impact here ends up being upwards of, in tests that I've done, an 80 to 90% reduction in the amount of header data sent back and forth, which is massive. The downside is that it does introduce the need to maintain state in the protocol. For every connection, every side of the connection, client to server, you have to maintain 2 separate state tables for each direction, your incoming state and your outgoing state. This is something HTTP1 just simply has not had to deal with in the past, and a lot of HTTP-based infrastructure has not had to do in the past. And it adds a significant new requirement for that infrastructure. So when you're planning for HTTP2, it's really important to make sure that your infrastructure, your intermediaries are set up to be able to do that. It can be a significant new memory management issue. So how this works with header compression, by delta encoding, what we mean is that the protocol only sends the differences. So the very first request, we're going to basically say, all right, we're going to use the get method, right? We're going to index that, but that has a statically known entry that's already assigned by the protocol. So that's just identified by the number 2. We're going to add a new header, ABC equals 1, 2, 3. This is something we came up with. It's not part of the static index. It's not known. So we're going to assign it a new value. We're adding it to our state table. It's going to be given the number 62, right? And then let's come up with another one, and we don't want to add it. It's going to change frequently, or it's sensitive data. We don't want to add it to memory. We just want to pass it as is. So that's XYZ 321, but it's marked explicitly as not indexed. We're going to pass that, and we're going to encode that in one of these header frames. And what we're going to say is we're going to add an index value, which we literally just pass as the number 2. We're going to say it's an index value number 2. We're going to say literal index. We're going to add a compressed for ABC equals 1, 2, 3, and then the not index will pass as the literal. This ends up getting compressed into a very, very small frame and sent over the wire. It's a fraction of the size of the data that would normally be sent over HP1. On the receiving side, they just update the state table accordingly and keep the two in sync. If these two tables ever get out of sync, the entire connection needs to be torn down, no matter how many connections you have, how many concurrent streams you have over a single connection. All of those streams share the same state tables for headers. So you can have, theoretically, 10,000 concurrent streams. They're all going to be synchronized using the same header state table. So it's very, very important to keep these things in sync and to ensure that those stay in sync throughout the life of the connection, or you have to tear it down and start over again. So next request comes along, and we want to say it's get again, and we want to change the value of ABC to 456, but we're going to use the XYZ again. Again, XYZ is not indexed. We're not storing that, so we have to pass that, and we're just using number 2 again. And then for the literal indexed, ABC, we already used the ABC name, so all we have to do is point back to that, but we're passing a new value, right? What that does is get added at the end with its own new value. Very, very important to keep this state, and it's something that HP1 has not had to deal with, and it's something that Node specifically has not had to deal with in the past. Node's implementation right now with HP1, when a request message is received, that first comes over the socket, goes into our JavaScript layer within core, and then the block of text that represents those headers is passed off to a C library that we bundle internally called HTTP parser. That goes through, and it's very specifically written to parse HP header text very, very efficiently. It is only written to support HTTP 1.1 style messages. It cannot be reused for HTTP 2 because of these differences in how headers are transmitted. Once those are parsed, the parsed header key values are passed back up to the JavaScript layer for use. HTTP 2, because of these protocol differences, ends up requiring a completely different implementation path. We cannot reuse any of that existing code within core to implement HTTP 2. I think there is one utility function that we're using that we're sharing between the two. Everything else is brand new code, and that is the way it will be going forward. So just to kind of recap on the Delta encoding, it does allow for very compact header transmission, like I said, up to about 80% that I've seen. A significant reduction in redundant data being passed back and forth. I have to say is probably one of the most critical features of the new protocol, but it also is one of the most complex aspects of implementation of the protocol. The HTTP2 request response flow. So I alluded to this a little bit earlier. Essentially what happens is that a client establishes a connection. The HTTP2 specification allows for plain text TCP connections and TLS secured connections. In practice, browser implementations require it to be over TLS. Node server will support, well, actually client and server will support opening both connections, but the TLS secured connection will be the default and the preferred. What this means is that when you're setting up a connection, you'll either set up the plain text, you'll set up the TLS. There will be a difference in how we establish or negotiate that HTTP2 is going to be used, and we're still working out the details on exactly how that will work. But once you get started, everything else will be identical between the two. Once that connection is bootstrapped, a client will initiate a request by opening a new stream. Opening a new stream is done by sending an initial headers frame with your request headers. Those are transmitted to the server. It could be followed by any number of data frames and optionally by some trailer header frames. The server will receive those, and using the exact same stream ID, we'll send a response by sending its own headers frame with the response headers followed by any number of data. It's rather straightforward, very familiar to anyone who's familiar with HP1 in general. Okay. After receiving the client-initiated odd numbered stream, server may choose to create its own even numbered streams. These are push. These can only be sent in response to a client-initiated request. What these are essentially assumed requests. For many websites, we have you request a page, and there's all these JavaScript or CSS or image files associated with additional resources. The server knows that those are going to be requested. It can either choose to sit and wait for the requested, or it can proactively start to send those. And a lot of times this is used by servers to prime HTTP caches. So if it knows that's going to be sent, it can start preempting that by sending these things. The client can say, all right, I already have it, and cancel it. But for the most part, it's server driven based on what it assumes the client is going to need. Going in, looking at the HP2 versus HP1 in Node Core. As I was talking about, the HP1 message flow essentially involves writing this just a sequence of text directly out to a socket. The code, if you look in the request object in in Node Core, if you look at the internals, what you'll find is that when you write a header or when you start writing data, the code is highly optimized just to eliminate as many layers as possible and allow that data to be written directly to the socket that's open. And there's many assumptions made for the sake of performance that there shouldn't be anything else in the way, right? Or no one else should be using that socket. You're just going to be writing the data. And then when you're done, you're able to move on. There are many more steps involved in supporting HP2. Not just reading the data off and writing it back. There's parsing the binary frames, updating header state tables, doing the Huffman decompression on the header data, reassembling the stream data. Again, everything is chunked into multiple frames. So there's a significant amount of context that has to happen, context management that has to happen in order to reassemble those. There's a significant amount of data caching that has to happen internally as well. To be able to reassemble the data and pass it back to the application layer. There's also flow control and prioritization that has to happen independently of the flow control and prioritization that happens at the TCP layer. So there are many things happening there, and a lot more that has to happen per tick of the node event loop, which means the performance profile of your applications is going to be drastically different than what you see in HTTP1 today. The performance really is going to vary, and we'll see. It's going to take quite a bit of benchmarking and experimentation for us to really nail down what a good performance benchmark is going to be for HP2 under Node Core. What we've decided to do, because of the differences in the protocol, is because they go down a completely new implementation path. HP2 will be a completely isolated set of code than HP1 in Core. We are using ng-http2 as a dependency and pulling this into Core. It is a C implementation with a very well-defined API. It is one of the best HP2 implementations available. It's the same one that's used by curl and a number of other projects. It's probably one of the most well-tested implementations out there, and definitely is one of the best performing implementations out there, independently of what we're doing in Node. The effort is to simply bolt it into Node Core. It fortunately takes care of most of these details. It handles all of the header compression. It handles all of the the state management for streams. It's taking care of the prioritization queue. All of the heavy lifting that I was just talking about with the protocol is happening internally by NG HTTP, which makes it ideal here. The other really nice thing with NG is that it doesn't do any of its own I/O, which means any of the communication that happens over the network, Node can handle that with its existing TCP implementation, and hand those details off as it receives the data and hands it off to NG for processing. NG does its thing, and then through a series of calls back into Node's code, and then we can pass that up to the JS layer, JavaScript layer. So the one thing that we have to consider, though, is that it has to be fast. Going back and forth between the JavaScript and the native code layer, there's always some issues with performance going back and forth across that layer. So we have to try to maximize the performance as much as possible, but and without killing the actual functionality. So HTTP2 implementation layers, how are we doing this? Again, we're bringing in NG HTTP2 as a dependency. We have some internal code to Node that implements essentially a glue layer between NG and Node. This is the piece that Node itself uses to implement these bits. This is not public API, so this is not something that the users should be using at all. Above that, there's going to be a core API, and this is going to be very, very minimal and very, very focused on HTTP as a protocol. This will expose an object like HTTP2 session, which is used to manage the communication session. For every session, there will be exactly one socket. It's a one-to-one relationship. Within that, there will be a class called HTTP2 stream that allows communication back and forth based on frames. The HTTP2 stream object will be a duplex implementation. So anyone familiar with the Streams API already in Node, this will be readily familiar with reading and writing data. There'll be a simple API for setting headers, reading the headers off, that kind of thing. But it is very, very focused on a minimal interface and will highly optimize for performance. The next layer above that will be the compatibility layer. This will be an API layer that is very familiar with the existing HTTP1 implementation in core. This is going to be layered on top of that minimal core and will be designed not necessarily to be the most performant, but it'll be designed to be the most familiar to existing Node developers who are using HTTP1. So there will be a request and response object. Creating a server will be very similar. The functions for setting headers or reading headers off will be very close. There will be some differences because of differences that exist in the protocol. For example, the status message on a response no longer exists in HTTP1 or HTTP2. So there are some API differences that will be there, but for the most part, the compatibility layer is designed to be as close and familiar as possible. And when everything is said and done, that will be available. Either one of the APIs, the core or the compatibility, will be available by doing a require HTTP2, which will become a new core module. Now, it should be noted that there is an existing module out on NPM today called HTTP2, and the author has offered to go ahead and give up that namespace for use by core. So we're definitely thankful, and we'll be working with them on a transition path to ensure that users of that module aren't adversely affected. But stay tuned on this. Some of the details of all of this may continue to evolve over time, but this is the current plan. So let's look at some actual code. This is always the fun part. The great news is we have this working. We can set up a functional HTTP2 server with Node today. And I would show a demo, it just doesn't come across too well in the webinar, but it is something that you can play with. I'll get to the GitHub repo in just a bit and show where you can get those details. But this is essentially what a server would look like. Very familiar with for anybody who has been using Node for a while to set up an HTTP server. We're just going to create the server, pass in some of the options. The options are going to be your typical options for setting up a TLS connection in Node. So your key information about your certificate authority and those kind of things, the algorithms you want to use. And instead of a request response, what we're showing here is the core API, so the more minimal. And at that level, you're dealing with the stream itself. So you receive a stream, you're going to receive some headers. You want to respond to just stream.respond, pass in your response, and then use the streams interface, the Node streams interface, with write and end to actually send the data back. And then we just say, tell the server to listen on a port, and off we go. Very minimal, and should be quite fast. Now on the client, we recently got the client working. We're still working on the API details for this, and it's something that we're going to continue working on for a while to make sure we get it right. But the client should be very similar. If you already do HP client work in core on Node, there shouldn't be anything too surprising here. We are using the new URL, WG URL implementation that's in core. So H2 connect to that URL. The important thing to keep in mind is that with HTTP2, you do not open a connection for every URL. You open one connection per host or per origin. So if, in this case, the only part of that URL that Connect is using is the HTTPS and the example.org portion. It's actually going to ignore the /foo. That will come in later on. Then we're going to say client on response and do, again, we're using the low-level interface, so it's, we're going to get the stream back, and we handle we can get the headers from there. Anyways, we receive data on that. We're using the typical streams, Node streams API for getting data, and everything from there should be fairly familiar. All of the details for the implementation for the API are still being worked out. What we need at this point, and what would be extremely helpful, is user input on what would be the most useful API. And if there's something that, if there's part of the direction that we're heading down that just doesn't seem to make sense, we would love input from the community on how to improve it. So to recap that, core low-level API based around HTTP2 session and stream will provide direct access to HTTP2 features. So push streams or the prioritization, flow control, those kind of things will be exposed directly through the core API. The compatibility API will hide quite a few of those HTTP2 features in order to provide an API that is very similar to what users have today with HTTP1. It will be close compatibility with existing code, but not 100%. So there will be some differences. And the key differences there will be whether you want faster access, your faster API versus a more familiar API. And it really will be your choice. Both APIs will be considered fully supported by core once they're done. So the timeline, let's talk a little bit about when we're going to be doing this. The intent is to land the support as experimental, unsupported feature in Node 8x. So we're a few weeks away from 8.0.0 being released, Node 8.0.0. The goal is to add this within probably about the June 2017 timeframe. I'm not sure what point release Node 8x will be on by that time, but because this implementation does not require any breaking changes to Node today, or to the Node HP implementation today, we will be able to add this at any point in time during 8x lifetime, with the goal of having it be a fully supported feature of Core by at least, or probably at the earliest would be 9x, but probably more realistically would be the 10.00 release. We are currently working on improving the API, adding tests. Tests is going to be the most significant piece of work right now. Adding documentation, and generally just making sure that it really does work with all the various edge cases, and running it through a variety of the test suites that exist for HB2 currently. We are testing against multiple browser implementations, and we are also testing it with curl and Nginx. The browser implementations are going to be the most critical. There is a tremendous amount of work still to do. Just the test suites alone is going to take quite some time to do. If you're looking to help, or looking to get involved with Node Core, helping build those tests, or helping with the documentation, or helping us refine the API is a fantastic way to get involved. And we would absolutely love to work with any one of you. The GitHub repo is right here on the screen. Is github.com/Node.js/HTTP2. Jump in, open a pull request, open issues. Let us know if it works. If you try it out and it completely fails, let us know. The repo there is a clone of, or it's a fork off of Node Core itself. The current implementation is just it's a bit older than what Node Master is right now, but you essentially build a new version of Node that has this in there, and then you can play around with it locally. Any questions on that, feel free to reach out and let me know. That's where we're going, and that's basically it. If there are any questions, I'm happy to take questions in the chat here. It looks like we have a couple of them. Let me see if I can actually pull it up. Let me see here. There we go. It's going to take me just a minute to pull up the list of questions here. The user interface is somewhat limited. Just 1 second. Looks like the question, are there any performance gains? Let's see. The question is there any performance gains with this implementation? So right now, we are currently benchmarking at about 30,000 requests per second in a peak load test. So this essentially throw as many requests at the server as we possibly can, as quickly as we possibly can, and make sure the server doesn't completely fall down. And with that, we are able to do about 30,000 requests. In comparison with the exact same test with HTTP1, with the current implementation, which has been optimized for years, we can get about 45,000 on the same test on the same machine. So we're at 30,000 without any real effort being put into optimization yet. We're just focusing on just the implementation. So the performance, we've got a ways to go. NG HTTP to the library has been benchmarked before to be able to do up to 100,000 requests. So we have a lot of room for improvements in the current implementation. Where HTTP really begins to shine is because of the multiplexing, the elimination of the head of line blocking. It maximizes the use of your connection bandwidth much more efficiently. Allows you to eliminate completely eliminate the need to do open multiple connections, and just manage that flow of data much more efficiently. So what you'll find in a real world scenario is that HB2 is much faster than with HB1, and it's much more efficient over the wire with the header compression and that kind of thing. we have a long ways to go with this particular implementation in terms of optimizing it, though, and it's going to take us a little while to get that performance profile correct. So hopefully that answers that question. Yeah, the very short version is there will be, but it's going to take a little while. So the next question is, currently using Nginx as a reverse proxy with HP2 TLS on the internet side. What advantages are there when talking HP2 between Node and Nginx? And what differences are there between this sort of environment and Node directly on the internet? Is TLS required with HP2? So this is this will be a significant thing. Node has never been a great TLS endpoint. And the reason is because of that event loop and the amount of computation that is required for TLS. It just doesn't perform very well. So it's very, very common to stick an Nginx server or any other TLS terminator in front of Node and just talk plain text, back to the Node server. What I suspect is that the same thing will be common here. Use Nginx or something else on the front end that can handle that TLS termination much more efficiently, and then open a plain text connection back to even the HP2 implementation in Node. That is likely what would achieve the greatest performance profile. Node will support either. It will allow you to do a TLS connection back, set up a TLS server, or you can do the plain text server. It really will be up to you. The advantages here would just be in helping manage that. Again, having much more efficient data flow back and forth between the two. It remains to be seen how much of a difference that would be. We have not fully benchmarked those differences, and that is a significant piece of work that we will be doing, and being able to compare what those profiles look like in real world applications. So not a great answer, but it's kind of where we're at in the current state of things. All right, let's see, next question. The second part of that is, will TLS be required? That's kind of forced on us. Browsers require TLS. So TLS support will be required at some point if you are serving HP2 to those clients. So, all right, will HP2 be the default for upcoming versions of the Express template? No. So Express is for one, it's a completely separate project from Core. What we're doing in Node Core and what they do in Express, those are completely different timelines. And Express tries to maintain as much as possible a focus on kind of the common denominator for as many projects as possible. And when they support older versions of Node, they try to provide a very minimal interface, very efficient interface. I have no doubt that the project there will adopt HP2 as we go along, but when that becomes the next kind of the default remains to be seen. I think the HP2 implementation is going to require a significant amount of proving out before it becomes the default. So that's where we're at there. Let's see if there's another question. I think we have time for just about one more. Let's see. Oh, that's what we have. All right, so we're at the end of the questions. I think that about wraps it up. If you have any other questions, feel free to let me know. I am J.A. Snell on Twitter. I'm J.A. Snell at GitHub as well. I'm happy to have any conversations about HP2 or Node Core. Even if you're looking at contributing to Node Core, not just on the HP2 stuff, feel free to reach out and let me know. I'm happy to hear from you. Thank you all very much for joining, and hope you all have a fantastic rest of your day. Goodbye.